let's get started today. I know Joel has a lot to cover today, so let's get started. As people arrive, I'll let them in the chat, or I'll let them in, and we'll continue to post the link in the chat. So I want to thank everybody. For attending today's workshop. Philly Codefest workshop series today is 3D data visualization with VTK. Joel Pepper, one of our doctoral students, he's volunteered to give this talk today to talk about VTK, the VTK library, and how to use data visualization and 3D graphics to enhance your Codefest project. So again, we've posted the link to the to Joel's GitHub information in the chat. I will post it there again. Sorry, the link is crazy, but I'll post it there again. So with that, I will turn things over to Joel. If you do have questions throughout the chat, feel free to put them in the chat, and I will monitor that, and we'll have some time at the end of the day for question and answer. So with that, Joel, take it away.
All right, thanks. Okay, let me share my screen. Okay, so yeah, my name is Joel, and I'm going to be covering how to use the 3D visualization toolkit for 3D data visualization. I will say this is going to be a somewhat more advanced workshop. It just kind of ended up that way with, you know, what I wanted to cover and sort of the nature of, doing a lecture on a more advanced library than just like a programming language or something, but we can get into it here. Okay, so kind of outline of what I'm going to go through. I'll give some background and kind of why you might want to use something like VTK. Participants can now see my screen. Okay. Give a introduction to VTK, give an introduction to the Qt application framework, which I use in my demos. Talk about how to initialize things in VTK, kind of some building blocks, some basic operations, things you can do with VTK. And then I have 3 demos. Since this is, couched within a hackathon, I wanted to show you how to use this in a few different languages. So I mostly work in C++, but then I also did demos in Python and JavaScript. Okay, so, it's a visualization toolkit. So we're talking about computer graphics here. So 3D computer graphics rendering is complex, tedious, and slow if you try to do it from scratch. Probably doesn't surprise anybody. Even with GPUs and things like OpenGL, DirectX, or especially Vulkan, which is even lower level, it still constitutes very low level systems programming with a lot of overhead to get things to happen. So this image I've included here is me, doing everything here from scratch for Professor Breen's advanced rendering course here at Drexel. So had to deal with generating the geometry and topology for primitive shapes like spheres and rectangular prisms, reading in triangle meshes, like CAD files and rendering those, doing things with the lighting, camera positioning, transformations, shading. I also have reflections. This one's a bit transparent, have some shadows in there. And, it's all just a monstrous undertaking to do it this way. And it's still a decent amount of work to do it with like OpenGL. So for something like data visualization, you want a higher level toolkit to simplify and accelerate the development process, which is, enter VTK. Okay, so here's some official examples from their website of what you can do with this software. So here's one where they read like a triangle mesh of a face in, and then they're visualizing the normals from this mesh with these little arrows here. Here's one showing kind of like airstream going around a cylindrical obstacle. Here's one for medical imaging where, they have an external image and an internal image and they're showing them together like that. And then here's one of a very large molecule or protein, something, where they actually there's a built-in molecule renderer with VTK. I'm not going to cover it, but there's tools like that to do common visualization tasks as well. Okay, so kind of the VTK workflow is where I'm going to start. I would highly recommend you download the demo code I have here, or I guess you could just look at it in GitHub too. You don't necessarily have to download it, just because I got to go through this pretty fast, and it's going to be easier, I think, if you have the files I'm talking about in front of you. But a VTK program consists of a scene of actors within a render window. And then this render window is, in the case of my Python and C++ demos, bound to a Qt framework actual desktop program. And there's only one of these. Technically, there can be more than one render associated with the render window. I'm not going to show that, but that's kind of why they're separate. So you need both. And then actors can be things like lines, curves, cubes, spheres, and triangle meshes. And actors are created via the following workflow. So you can start with a source object, which is used to generate the geometry and topology of well-defined shapes. If you don't know what I mean by topology, it means the interconnection between vertices. So like the triangles that are connecting the geometry, which is just vertices. But a source can be used to generate things like cubes and spheres and cylinders and stuff like that. A reader is used to read geometry and topology from CAD files, and we'll see that as well. Filters are used to manipulate data objects. They're not always explicitly needed, and I'm not going to talk about them very much here. I do have one in one of my demos, but they're there to kind of mutate the information coming from a source or a reader if that's something you need to do. A mapper converts basic geometry definitions to rendering. So like what you get from a sphere source isn't actually something you could draw to the screen. You need to map it into something that whatever your graphics backend is, OpenGL or something like that, can actually handle and get it up on your monitor. And then finally, actors are renderable objects that contain all geometry, topology, and visual properties needed to draw something in the scene. Okay, so a little bit of sidestep here. I'm going to talk about the Qt application framework. So VTK does include things like buttons, sliders, input fields, text boxes via what it refers to as widgets, and can be used standalone to create more or less fully fledged GUI programs. However, widgets are rendered on top of or even inside of a VTK scene, and their configuration is, I think, kind of clunky. So in order to more easily create traditional desktop applications, you want to use an application framework, and I'm going to cover a very basic intro to Qt, which I found out recently is pronounced Qt, not Qt. Anyways, so the easiest way to use Qt is to create .ui files with a program called Qt Creator. So here's a screenshot of what that program looks like, and here's a UI file that I have set up for my C++ demo. The clear entity that I have clicked on is where the actual VTK scene gets rendered to. So that's what gets bound to the render window. And then I also have a few buttons in an area to print text. So Qt is based heavily around something called the meta object system, or MOC. And this is a framework and an executable that takes special Qt-enabled C++ programs as input and converts them to valid C++ code with additional Qt features. In addition to processing UI files into C++ code, MOC also enables signals and slots for inter-object communication. So for example, it lets you do things like a button press can trigger a function to run, or a non-blocking timer can call a specific function every so many milliseconds. So here's what some MOC code looks like, and this file is in the C++ folder, and then in there it's in the source folder, and it's called mainwindow.h in my GitHub repo. So this is how you define something that Qt is going to be able to draw to your desktop environment. So we define a class main window that subclasses Q main window, which is what it sounds like. It's the main Qt window. And then you need to include this Q object kind of keyword, which that tells MOC to add in a bunch of extra, special Q functionality that's needed to actually, run the environment, and kind of tells it, hey, this class you need to process. And then the other important thing in here that mock takes care of is these queue slots, which these are special functions that get called by queue entities. So like this first one gets called by a queue timer, and these other ones have a special naming convention where they're called on pause button clicked. That naming of a slot tells mock to link this function to the pause button I defined in the UI file to run, this function when it's clicked on, and does the same down there. So you don't have to link any of that stuff up yourself. You just follow the mock conventions, and then it takes care of all that linking stuff for you. Okay, so the main Qt runner code is actually pretty short. You just need to create a Qt application, create an instance of your main window, show it, and then pass control over to the Qt application. And that's all you have to do to get a Qt window on the screen. So very quick side note, I don't have time to talk about this much, but when you're working with complex libraries like, Qt and VTK, you pretty much need some sort of automated build system. And for the C++, I'm using CMake, which if you've never seen it before, this is kind of like a meta configuration script that's like a step above a make file. So this handles things like finding where the libraries you want to use are located, setting compilation flags, defining information. This here like handles setting up mock to run, all that kind of stuff. And then you compile this to a make file, which you then actually run. So if you've never seen this before, I have execution instructions in the repository, but that's another step of the process in here. Okay, so back to VTK. I'm going to talk about things that need initially set up pretty much every time you use it. So a handful of VTK objects need to be initialized once and then are reused in most operations. And you always need a renderer and a render window. And for the demo I made, we also want a file exporter and a render window interactor. So again, this is coming from these files. So these four things, I need to have it be stored as instance variables of my main window class, so I can, reuse them throughout that class's code. So they need to be defined here in the header file. And the first one we're going to talk about is the renderer, which you initialize this way. So for C++ with VTK, pretty much everything VTK related is wrapped in this VTK smart pointer template here, and then you say the actual class you're referencing over here. It's just a pointer, but it comes with extra functionality like this new function that initializes VTK objects. So if that's confusing, don't worry too much about it. It's just they use this wrapper to add extra functionality to their pointers. But then with the render initialized, you can set the background color and then add it to the render window, like I said, you need to do. And then for the render window, specify it the same way here using an OpenGL backend is what we're saying up there. Initialize it the same way with that new call. And then this one needs bound to the actual Qt entity that I'd set up for it. So this UI refers to things from that UI file. So that QVTK widget that I created in there, you set the render window to the render window, and that gets that bound up so you can actually, see things. Next up is a file exporter. So that once again is a new call. You set the render, you set the render window, you set the file name you want, and then you're good to use that. So what that allows you to do is export your whole scene that you have into, in this case, an OBJ file that you could open in something like, say, Blender if you wanted to. And then last one here is the render window interactor, which allows you to handle and process like user click or other types of events within a VTK window. So in this case, the render window already has one, so we just get it. And then we need to set up what's called a callback command. So this takes a function here, this click callback function that it calls when a certain event happens. So down here, we add an observer for a left button press event to this callback. And then when that happens, it'll call this function. This VTK new syntax, if you don't need something associated like this up here, where you have to declare it first, this VTK new takes care of calling this new function and accomplishes the same thing with, less characters. So this is kind of syntactic sugar for instantiating a VTK object. And then one other thing that needs to happen is this click callback function just has to be a regular function, not an instance method for the class. So what we need to do is associate this main window instance with this click callback through this kind of syntax so that we can access things from the main window instance within this callback command. And we'll see more of that once I get further down in the demo. But so that's the initialization part. So now I'm going to cover what I'm calling, building blocks for VTK. So, cover a few different ways of creating actors, exporting VTK scenes, handling events, and then picking of actors via mouse clicks, where you get the actor closest to the camera under where you clicked with your mouse within the scene. Okay, so here's how you, from a cube source, are able to make a cube. So VTK new cube source, get a cube source. And then I, in this case, set the bounds to be negative 20 to 20 in X, negative 10 to 10 in Y, and negative 10 to 100 in Z. And then, like I said, that just gives you basic geometry topology. So then you need a mapper to make it actually something that, is renderable. So how you deal with that is have mapper.set or arrow set input connection, cube source, get output port. So you're creating like a chain that flows up through all the different pieces needed for VTK. So then we have that mapping. Now we need an actual actor. So we make a cube actor. We set the mapper to this guy, which has the source set to this guy, set the color. And then I'm also making it mostly transparent. So if the opacity is 1, it's totally opaque. And if it's 0, it's invisible. So once I get to the C++ demo, this is supposed to represent a river that fish are swimming through, but we'll get there. And then finally, actors always need added to the renderer so that it knows to actually draw them. Okay, so here's for a sphere. It's pretty much the same thing, except you can set the radius of the sphere and then phi and theta resolutions, which, if you don't have much exposure to computer graphics, everything with a GPU is, triangles when you're talking about something in 3-dimensional space. It's just triangles. There's no other shapes it processes. So these things tell how many triangles to use in each direction when drawing the sphere. So if you set it to 1 and look at that side, it just looks like a triangle. If you set them both to 10, you can tell it's a little bit blocky, but it's still a sphere. And then, this one's looking at the 20 side here, so you can see it gets a little bit less blocky with a higher theta resolution. Again, if you don't know anything about computer graphics, drawback to that is more triangles means more oomph needed to process them all. So if you have 10,000 spheres on your screen, you're going to want to use as few triangles for them as possible. But that's getting a bit far afield. Okay, so then the mapper and the actor stuff is the same as the cube. Okay, so here's a curve. This one's decidedly different. So if you want to draw a cube from a list of points that define, or a curve from the list of points that define it, this is kind of the process that can take. So in this case, I have a point list. I need a VTK points object to store those in. So this is just a JavaScript object, a JSON object, not a JavaScript object, that contains an array of 3-dimensional points. So just, accept that that's what we're getting here is 3D points with each of these point guys. So what we want to do is insert all of those into the VTK points. And then that gives us, base geometry there, just a bunch of vertices. So now what we want to do is use this VTK polyline to create an object that contains a bunch of little line segments all going around connecting each of the vertices. So first we need to tell it how many points we're going to have, and then the points are already in order. We're not bouncing around in this list. So we just say that at index 0 within this polyline, use index 0 of points, and that's what that's doing. So now with that settled, this may get a little bit confusing, but we need to feed that into a VTK cell array. And what cells are in VTK is things like a line in one dimensions, or a triangle in like 3D, or even like a quad, it has 4 vertices associated with. There's some sort of connection, some sort of topology. So in this case, the topology is just a bunch of line segments in 3D space. So in order to set that up, you say cells, insert next cell, and then the polyline, and that takes care of it. So then you have points defined, and you have cells, which are line segments defined here. So now we need to put them together into one object. That's actually is what's going to be mapped forward to the actor. So that's what VTK polydata is for. So for this one, you set the points to the points and the lines to the cells, and that defines both our geometry and our topology. So now we get to the point where it's the same again. So we have a mapper, we set the input, we have an actor, we set the color, add to the renderer, and then boom, you get kind of this curly cube, which is how I had the points defined here. Okay, so this one's kind of extra. You don't have to worry about this one too much, but if you want to do a triangle mesh directly from vertices and faces, this is kind of how you do that. So just, accept that I have my vertices in here and my faces in here, and we want to set up basically the same thing, but now with triangles instead of line segments. So we define points again, and we insert the points again. That's about the same. Now here, this cell array is about the same, but we're setting up triangles now and inserting those instead of line segments. So now we have the topology defined here and the geometry defined here. We need to put them together into polydata again, and then it's the same again. And then here's this cow that came out of these verts and faces matrices. But you're probably not going to do that. I had a special reason for even having to put code like that together in a different project. But what's more realistic is just to import CAD files with a reader. So my C++ demo is based around fish swimming through a little polygon river. So what I want to do is import my fish CAD files that I have. So this is looping over those as they're defined in a JSON file, which I'll show that in a little bit. But we need an OBJ importer because they're all 3 OBJ files. We need to set up a file name. They're stored one directory up, and then in this directory, then there's the file name, there's their extension. For the import, you set the file name, you set the render window where you want them to go, and then you run update. And then you get these polygon meshes with their shading properties. If you know anything like about the Phong model or computer graphics, like those OBJ files have an MTL file that defines their shading properties, and then these ones also have a texture file that gets mapped onto them, so they look like fish. And doing this texture mapping, all this in just base OpenGL is pretty tedious, so it's nice to get this all for free with these OBJ importers. You can also export CAD files. It's basically the same thing, but here I make an exporter, and then set the rendering stuff, set the file name, and then run update. And here's that cow that I just had defined in Matrices. I now exported it as an OBJ file and opened it in a CAD program. So you can see how this kind of stuff can be fed back into animation or computer-aided design or something like that. Okay, last of the building blocks here is event handling. So here's this click callback function that I mentioned earlier. The VTK click callback command thing expects an exact signature for these callback functions. So it has to be VTK object caller, and then client data is down here, which is where I bound that main window, which I need information from inside of this just regular non-instanced function that gets put in there. So we can get the main window by casting, if you're not really if you mostly work in scripting languages, you might not be used to this, but everything's very strict type. So like this is strictly typed as a VTK object pointer. So we need to reinterpret that as a render window interactor, which we know that it's that, so this will work. And then we need to reinterpret the void pointer, because you can bind whatever you want here, as a main window, and then we get access to both those things. And then the interactor knows where the user clicked within the VTK scene, and we can get the click position through this syntax, and then you can print it, which I do. And then what we want to do is pick which fish we clicked on for this specific fish related demo. So we need, in this case, we need a VTK prop picker. So we set that up. This is kind of a long form way of getting the renderer. It's directly associated with the main window, but if you don't pass that in, this is how you get it from the interactor instead. I just left it like that. It's a little long, but then we want to do something, again, a little bit funky. It'll make more sense once I show you the demo, but my fish that I want to be able to click on are inside that translucent cube from earlier. So I don't want to pick against that. So what I'm doing here is I'm getting my cube, I'm removing it, I'm doing the picking, and then I'm putting it back. And this call here actually deletes the cube, so I need to copy it and then put the copy back. There's an arguably more elegant way to do this where you set up like an array of actors, and then you pass that into this pick function. But for my purposes, this was, probably less code. So this is just what I'm doing. And then once we get that back, we have potentially a location within the actual scene coordinates, not the XY of the pixels in our frame, but the actual scene coordinates of where we clicked, and we can print that. And then we potentially have an actor that was clicked on. So if it's null pointer, we didn't click on an actor. But if we have it, we can print out which actor we clicked on. And then for my demo, what I'm doing with this picking is in a text box, I am showing information about that specific fish that you clicked on. So that's what this is doing. And we'll see that once I get to the demo, which I'm there. Okay. So now that was all the information about VTK that I had to share. I know there was breakneck pace, but yeah, now I have my demos that I can show, and hopefully these are set up in such a way. I tried to set them up in such a way that they're as easy to use as possible, and potentially also something you could build off of for the hackathon. So anyways, first demo is in C++, and it's based around visualizing data on fish swimming patterns that I just made up and generated myself. It's not real data. 3 fish are defined in a JSON file with their models, some transformations on those models, info about the species, and the path they swim. So the visualization aspect includes rendering a translucent box to represent a river, loading fish models, fitting curves to the swim paths, then animating the fish models along those paths. So picking of fish is also included to show their information in Qt window, like I talked about. And then I also have some basic functionality bound to some buttons. Okay, so get that out of the way for a second. Okay, so here's that demo, VTK for free. The render window gives you the ability to like pan, zoom, rotate, which is not free if you're using OpenGL. You have to set all that stuff up yourself. So that's kind of nice. But you can see I loaded in my fish. I loaded in the paths they take as curves, and the fish are swimming along their curves. being visualized, I suppose. So I can pause this scene here, and if I click on this fish, I got this information from Wikipedia. This text box shows the information about the fish that was picked. And over here, you can see when I don't click on something, the pick position is 0. There's no actor picked. But when I pick something, we actually get positions back in scene coordinates and a pointer to whichever actor we clicked on. And the outer cube is correctly being ignored. But I can switch between them like that. Start the scene back up again, keep them going. This centers the scene, so if I zoom around, I can get it back centered. One side effect to my laziness is that if you click on a line, which is really hard to do, but if you succeed, it says fish info not found. It's really hard to click on those lines, but to avoid that, you would do what I said, where you just store the fish in a collection and then pass that in, but that's minor details. Okay, so that's my kind of animated fish demo there. So now I'll kind of show what files we're working off of. So I generated this JSON file that contains, fish 1, there's also fish 2, fish 3, and information about it, like what its model file is called, what its information is, and what path it swims. So it's just a bunch of points. And then I also have rotations in the model in X, Y, and what scale it needs to be, because the models were not all on the same scale or rotation. I generated this in the CPP directory. There's another directory called Python helper. That's where I generated this from. I'm not going to show that. The code's not very interesting, but that's where I got it from. I made it that way. Okay, so now I'm going to quickly go, because I couldn't fit all this in the slides. So I'm going to quickly just talk through this main window.cpp file, which I'd recommend you open one way or another as well. So first thing you need to do, set up the UI file. This defines a cute timer for moving the fish. You have the slot, which is the move fish function, and then you have the signal, which is a timer that has this interval, which I set up down lower. But that's how I'm moving the fish that way. I'm just using like a JSON library that's included with my project. It behaves pretty much exactly how you'd expect a JSON library to behave, so I'm not talking too much about it, but I open my JSON file and I read it into a JSON object, and then I have that information. Talked about this, this is initializing everything. This is adding the fish models. This was not in the slide, so this is reading the information from that JavaScript or JSON file I opened. So we loop over the actors that I've added to my scene, which are my fish. And then we get the fish. One of them is transparent for some reason, so force them all to be opaque, do the rotation in Y and X, and set the scale from the JSON file. And then store the fish in like a vector just for convenience, also with its name. So like fish 1, fish 2, fish 3, which I need later down in the code to reference something, which I'll get there in a second. Here's setting up the paths. Already, that was in the slides. I'm going to talk about that. Here's setting up the river box. That was in the slides. Exporter. So that was all in the slides. Okay, so the move fish function loops through the fish I have, this fish vec I made, and we need the name of the fish, which is the second thing in the tuple I put in, and then we also need to know how many points there are in the path, which I just defined on the first fish. I only need to define it once. I'm just assuming all the paths are the same length, which they are. And then finally, with all that out of the way, we can actually get the fish, set its position to the X, Y, and Z of the point we're on in the path for that fish. And then I have a counter here that I update and modulus off the length, so they go back to the beginning instead of breaking. They go back to the beginning. And then you need to call render window render anytime you do something like that. Otherwise, you're not going to see the scene update. Here's my callback function for clicking. you know, we talked about this in the slides, so that's all from there. That's not too interesting. I just have to make in here, I have to make a couple things that are private accessible with those functions. Don't need to worry about that, you know. And then these are functions that are bound to those button presses. So like if the timer's active, when you click the pause button, you want to stop it and change the text to start, and then otherwise, you know, do the opposite. This just resets the camera, and this exports the scene, which doesn't really work with transparency very well at all. This kind of helps, but not really. So I'm not going to show this scene. I'm going to show a different scene. Yeah, so that's my C++ demo. In order to not run over on time, I just kind of have to keep plugging along. So now I'm going to show you my Python demo. So this demo visualizes building height data I got from the internet. I took about 2,000 buildings in Philadelphia that are in Philadelphia and sent them through an address to latitude longitude converter. And then I graphed the buildings as rectangles in VTK. There's also a very rough outline of Philadelphia in the scene that I generated just by clicking around the outline of town on Google Maps. So that's very rough outline. And the buildings can be clicked on, they can be picked to show their information in a Qt text box. So we'll get to that demo now. Okay, so here's my roughly Eagles colored green outline of Philadelphia. And then here's my, you know, random 2,000 buildings. You know, I had a file with basically every building in town, but it was too many buildings, and the converter, the latitude longitude thing, only let me convert so many things for free. But here's my buildings in here. Look at this one. So the brown here is the base elevation. So like this is how high the ground is at that building. And then the silver is the height of the building itself. So like if I click on this building, you can see that's 1901 North 13th Street, and its ground elevation is 80 foot and the building is 5 stories. And you know, you can plop this into Google Maps and verify that. Like these really tall buildings, you know, ironically, I thought this was kind of funny. This was just random location data. You know, obviously it's clumped, but this is Temple's campus. Like of all the things in the city to highlight, the random choice area was Temple's campus. So these really tall buildings are their dorms and research towers that have big T's on them. So that's kind of that area. And then over here, it's a lot more residential, like single family. So a lot of these buildings, most of these buildings are either 10 or 20, you know, either one or 2 stories. And I'm not doing anything with like how wide buildings are. So they kind of overlap, but you know, whatever, it's not that important. And then this scene, I can reset the camera. This scene, I will show you the export because it actually kind of works. So if I export that scene and open it up in a, oh yeah, that doesn't work, in a CAD program, you can see for some reason the outline loses its color, but this is hard to rotate. It's really hard to rotate. But the buildings are all there and they actually keep their color. So like this OBJ file could, like I said before, be open in Blender if there was some sort of animation or some sort of video rendering you wanted to do with it. So that's a real nice feature, I think, that you get for whatever for free. It comes with VTK as part of VTK. Okay, so this is the data file I'm reading this from. It's just a CSV file with latitude, longitude, address, etc. So that's where I'm getting that from. Here's, you know, the Python demo code. I stuck with Qt5. There is Qt6, but VTK really doesn't work with it. You know, they claim it kind of does, but I have not succeeded. So sticking with Qt5 here. We do basically the same thing. You know, you subclass Q main window, have a constructor for the thing where you do most of the work. In this case, this is a little different. We're not compiling the UI file or anything like that. We're just loading it dynamically every time and associating its contents with this instance of the main window. So that's a little bit different. Something else a little bit different is I could not figure out a way to actually put the VTK like render window directly into the UI file and make it compatible with PyQt5. They were just not getting along. So I figured out how to make it dynamically. And then I put a frame into the UI file, which just I'd hold stuff, you know, and I stuck the render window in there and then made it the same size as the frame. So it accomplishes the same thing. If that doesn't make sense, don't worry about it, but that's a little different. This is all the same. This is setting this up. Here's where I store the building information. So I read in the main data file, and then I loop over every line because every line is one building. And I make a cube source. This is for the ground. I say roughly how big I want, you know, the buildings to be, like X by Y. And then this file is in feet, but my scene is in latitude and longitude. So this lambda here converts roughly from feet to latitude and longitude equivalents. And then, you know, that was a little hard to see, so I scale it by 10. You know, that's why I wrote it like that, because this is a scale factor. But then I get the height of the ground, you know, the base elevation, and I set the bounds on that cube to be based on the A, and we actually have to go negative. So negative height that I got here. It's just how the scene ended up set up. I need to go into the negative for it. Set the location we need. Have to set an offset because it's the center of the prism. And then we're back to, you know, mapper, actor, add it to the render, and then do basically the same thing for the building, almost identical. And then here's how I define a big string with all the information from that CSV file. You know, it's just all plunked in there, and then I store it and I associate it with the actor for picking purposes, because when I pick the actor, I can then use it to index the info hash table and get this information back. This is just reading the very basic outline that I have. They're just latitude, longitude points, and then, you know, make a curve. We already talked about that. This is a little bit different. If you haven't written much Python, this is also true of JavaScript, but I don't use it. This functions in Python are objects, so I can just directly associate the things I need with them. I don't need to set up that like client data thing. So I want the render, I just associate it with the function. I want my info hash table, I just associate it. Same with this box. And then adding an observer is easier too. You just use a string and the callback function. You know, here's setting the buttons, the exporter, we've seen that. I had to, this is reset to a custom location, just because the coordinate frame I needed to look in a different way than it wants me to look. So I have a custom reset camera function there. Here's the picker. It's basically the same as the C++ demo. It does almost the same thing. This is pretty much the same. So yeah, that's two demos there. Let's see, you know, I hope you guys have had exposure to at least one of the languages I used here. But now we're on to the JavaScript demo, which is the smallest and will take me the least time to get through. But in this demo, I show how to dynamically generate a 3D, I'm calling it a network graph, using VTK.js, which is a full re-implementation of VTK into JavaScript. Like the Python one is just a wrapper around the C++ VTK. This is a totally different thing. But buttons can be used to add or remove nodes from the network, and the connections are also added and severed appropriately. So let me get my thing out of the way. And okay, so here is that open. And you know, if you look in my Git repo, you'll see I have crazy installation instructions for all the dependencies that may or may not work for you for the Python and C++ demos. They're difficult dependencies to install, and there's a lot of them. For this, it just runs. You literally just have to open the HTML file and it'll work for you. So that's nice. So here we have our scene. There's nothing in it right now, but when I click add new node, we get a node in there, and this represents, you know, something in the network. Hit another one, we get a connection between them and another node. Add another one. These are just being randomly positioned, and they're also being randomly connected with each other. So they can just, once there's more than two, they can be connected however. And, we're dynamically setting up kind of a network visualization here. And ideally, you would have a file with these things in them. You wouldn't just be making up data, but I am making up data. So now, great, we're adding nodes. This button removes the last node you added. So that guy's going to go away. And it also removes the connection you made. And I have the camera set up to auto adjust as you remove and add things. So that removes the last node. It can also remove the first node, which that will create disconnects in the graph because it removes all the cylinders, all the tubes there. So you see, this guy's now orphaned as you remove those guys. So that's kind of interesting. But with VTK.js, you still get all the panning and whatever else. Hold shift and you move around and whip it over there, and I can still reset the camera. So that's the JavaScript demo. So HTML file for that is pretty simple. Here's the actual inclusion of VTK from a content distribution network. So you don't have to install anything. This takes care of pulling everything in. And then my body is just a column where this is where the VTK render area is going to go. And then this has my buttons in it. And then there's my actual custom JavaScript code, which I have here. So, similar to the other thing, just to make things more succinct, I set up all these constants associated with the entities from VTK that I need. Initialize everything. It's pretty similar. You make a render window, you make a renderer, you add them. This specifies, use the WebGL backend. I don't think there's probably not even an alternative to that, but you add that into, that's slightly different. And then to tell it where in the scene to put my VTK stuff, I have object selector, a DOM selector for that VTK guy. And then I tell it, set the container to be that div. And I have a tiny little CSS file that kind of scales and formats these things, but it's not worth showing really. I got to set the right sizing for stuff. Set an interactor. In this case, I don't actually have any picking or anything or callback functions. You need this in order to specify how to pan around the scene and stuff, because the default for VTK.js is really annoying. So you want to specify this one. Okay, so we have spheres in the scene and we have tubes in the scene, and I need convenient storage to be able to access and deal with those guys. So that's what that is. And then, if you know JavaScript, everything gets bound to an event listener. So for all my buttons, I have different event listeners that do the operations I want them to. So we have the add node button. I define an area from 0, 0, 0 to 30, 30, 30 where the spheres can spawn in. Set the radius, make a sphere, set their center randomly, make a mapper, blah, 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 put the sphere in. And then I save the sphere in my array for use later. Okay, so now I need to make a tube connection to some other random node if there's more than one sphere in the scene. So to do that, I need a line source. This is different than anything I had in the slides. I didn't show how to, I don't think I showed how to make a tube, but anyways, we set, this is not a polyline, so there's only 0.1 and 0.2. So we set 0.1 to be the sphere we just made center. And then we either pick a random point, or if there's only two spheres, we just pick the other point. And then we set that center. And yeah, resolution update. Okay, so now here's the only instance of filter in my whole thing. Like I said, this is used to mutate source data. So what's happening here is our source is just a line with no thickness. So this tube filter gives it thickness. So we create this filter, set the input connection, set the triangulation, and then set the radius, which is the important thing. So now we have a cylinder of radius 0.2 instead of a line with no thickness. And then we're back to the same, but instead we now bind the filter to the mapper instead of directly binding the source to the mapper. Okay, so now we want to store all of the tubes associated with an actor in the tube thing at the same index so that we can access them together later. So that's what's happening there at the scene. And that's the meat of adding things. So whatever, it's reset camera. We also have removal. So I have one remove function that I either call on the beginning or on the end. And what that does is if there's more than one sphere, or if there's spheres at all, I guess, we remove whichever one we want to remove. So either the first or the last, depending on what index was passed in, get the tubes that are associated with it, remove them all, remove the actor, and then reset. Okay, so yeah, that was probably a whirlwind, but oopsies. But that's what I got for VTK. Well, I'll say it took 45 minutes. We started a little late. So yeah, so there's of course a ton more you can do with VTK, but this should give you a good starting point for making use of it. And yeah, I got, I don't know, at least 9 minutes for questions. I can stay late if somebody's got some serious questions or is really thinking about using this. But yeah, thanks for coming.
Thank you, Joel. This was great. Anybody have any questions? Feel free to shout it out, unmute yourself, or write it in the chat.
Let me see. I can reshare if I want to.
And I will say that if you are competing at Codefest, I don't know how many of you have competed in a hackathon before, but one of the things that really helps projects stand out is graphics. The judges, and we understand that in the course of a week or 2 days or 3 days, however long the hackathon is, you're not going to have a finished product. But if you can have something that stands out, if you can show something that looks good and explain how you got there, that really helps stand out from other projects. So this will definitely give you an edge when building out your project if you can show some graphics and show some cool things and explain how you got there.
Does anyone have any previous exposure to computer graphics or any particular interest in it? I didn't necessarily, plan to do graphics when I came to PhD, but it's interesting stuff. It's kind of fun to generate, pictures as opposed to, a lot of the work people do is pretty serious, just statistical machine learning, where there's not a lot to look at. It's just kind of error messages and like, why isn't this working, which obviously you get with graphics too, but I think it's kind of entertaining, the final result being a scene or some model. It's kind of fun.
Any questions or comments, or are we good to let Joel go?
Yeah, I mean, VTK has a lot of good examples. They're just straight up like start to finish tutorials aren't great. You kind of have to, if you want to get into this, obviously I think my tutorials, pretty clear. If you have the background, I'm kind of assuming a lot here, but if you have that background, gives a good start to finish explanation. But a lot of this I learned just from finding relevant examples and putting them together. But it's pretty powerful software. I think it's worth the time investment if you're interested in this kind of thing, to learn how to use it.
Any other questions? All right. With that, so Joel, thank you so much for this. This has been really helpful and a lot of detail, a lot of information. It's a really good technical workshop. So thank you again. For anybody who wants to go back and view this, this will be uploaded onto YouTube probably this weekend. But if you do want to view it, just let me know. Just shoot me an email and I can certainly send it to you in advance. If you have any questions, feel free to reach out to me. My email is dr366, and I can certainly put you in touch with Joel if you do have more questions. And we look forward to seeing everybody at Codefest in a couple weeks. So thanks, everyone. Look forward to seeing you all soon.